In this retrosynthesis example, the first thing we notice is that we have 8 carbons in the product, 4 carbons in the beginning over here. Somehow we have to connect carbons together, and the first thought is usually a Grignard reaction. That's what a very common way to connect carbons. I'm going to draw my squiggly line right over here. Number this 1, 2, 3, 4. And then we'll see about this side over here. The reason why I'm numbering that is because if I were to break this off as a Grignard reaction, I could, retrosynthetically, I need to have something where this carbon is negatively charged, carbon number 2. And over here, this carbon would be positively charged, or even delta, even slightly positive over here. So I have to have something of this effect. So now this compound here can come from a Grignard reagent. Retrosynthetically, that would be analogous to an MgBr, because the Grignard reagent 1, 2, 3, 4. Grignard reagent is a carbon nucleophile. The magnesium wants nothing to do with the electrons, so it's going to deposit the electrons onto that carbon. That carbon then becomes nucleophilic. And over here, retrosynthetically, this could have come from something where this would have been an epoxide. So with practice, a protonated epoxide. So now the question is, how can we make an epoxide? How can we make this Grignard reagent here? To make a Grignard reagent, no problem. We would just get this compound right here, go ahead, add magnesium to it in the presence of ether, the solvent. The magnesium has 2 valence electrons. It inserts itself into this bond, and now we have our MgBr Grignard reagent. No problem right there. So I'm going to circle that. That's one of our reagents. And then the other one is, how do we make an epoxide? This is a starting material to make an epoxide. So again, retrosynthetically, this would have had to have come from an epoxide. And to make an epoxide, we need to have one very efficient way of making it is to have a carbon-carbon double bond over here. Now they're not showing stereochemistry, so this is rotating around, so we don't know if this is really a cis double bond or a trans double bond. It really does not matter because eventually we're going to have no stereochemistry right there. And this would be MCPBA to go ahead and make that. If they were to show stereochemistry on the final product over here, then we would have to sit here and think a little bit about which one of these alkenes we would have to epoxidize. And then a precursor to an alkene would be an elimination reaction, where we have a bromine over here, hydrogen right there, use a very strong base. Now we do want to get the more substituted alkene, so we're going to use a small base, something like a methoxide. This will go ahead and do our E2 reaction. Thinking out loud, if we had a large base, then a bulky base, that would deprotonate and give us the less substituted alkene. And there we go. So when all is said and done, we have one reaction to make the Grignard reagent, and then we have this set of reactions over here to make the epoxide, and then we put them back together there. So I guess actually technically going forward here, no, we're okay. So that's our retrosynthesis.